welcome to lecture series. In my last lecture, we have introduced the concept of direct sum decomposition of the space, direct sum of subspaces, and we have seen if I consider the projection operator on a vector space, then projection operator also split the space into direct sum of two subspaces. We have seen if capital E is a projection operator, the projection of a vector space capital V, which is defined over F and V is finite dimensional then V is equal to, we have seen as R plus N, where R is range of E and capital N is null space of the operator E, please. So, if B1 equal to alpha 1, alpha 2, alpha r and B2 is equal to alpha r plus 1 to alpha n be order bases of r and n respectively, then the matrix representation of the operator E with respect to order basis B, which is basically B1 and B2, will be of the form of R cross R identity matrix, then 0, 0, 0, because E of alpha r plus 1 equal to 0, E of alpha n equal to 0, because they are all element of the B2. B2 is the order basis for null space. So, therefore, the matrix representation of E will be of this structure. It is very simplified structure, please. Anyhow, we shall utilize this simplified structure to simplify our original operator, please. So, to move in that directions, I will see that how this projection operator helps to decompose the spaces, please. So, to talk in that directions, let me first consider V be a finite dimensional vector space over the field capital F. Let V is direct sum of W1 plus W2 plus Wk. Suppose this information is given to us. Is it possible to introduce projection operator of the vector space V, where the range space of the different projection operator will be W1, W2, Wk, etc. So, let us see whether we can, using this direct sum decomposition of the space V, can I obtain a linear operator. Okay. So, let me define a function Ej from V to V as below. Okay. From start we have for any alpha belongs to V, I will have alpha is equal to alpha 1 plus alpha 2 plus alpha k, where alpha I belongs to W I, and this expression is unique. This expression is unique. Why? Because if not, let alpha also equal to beta 1 plus beta 2 plus beta k, then we have alpha 1 minus beta 1 plus alpha 2 minus beta 2 plus alpha k minus beta k must be equal to 0. This implies that alpha I minus beta I equal to 0 for I equal to 1 to k, since V is direct sum of subspaces W1 to Wk. So, this implies that for any element alpha belongs to V, I will have basically a unique representations like this thing. Consider Ej from V to V, Ej of alpha equal to alpha j, Ej of alpha equal to alpha j. So, this implies that the range of Ej is Wj, range of Ej is Wj, and null space of Ej is sum of subspaces W1 plus W2 plus Wj minus 1 plus Wj plus 1 plus Wk. So, this is the null space of Ej, please. So, for I not equal to j, Ei operating on again Ej alpha will be equal to how much? Ei operating on alpha j, so certainly equal to 0, since alpha j belongs to Wj, and Wj is basically the part of the null space of Ei, and null space of Ei is W1 plus Wj plus Wi minus 1 plus Wi plus 1 plus Wk. So, this ones, so this implies Ei into Ej equal to 0 for I not equal to j, and Ej operating on Ej alpha will be again, will have, Ej alpha is equal to, I have written this is equal to alpha j. So, Ej alpha j, which is equal to also Ej operating on alpha, please. So, this implies that Ej square is equal to Ej, please. Ej is a projection operator, the projection operator of the vector space V, and the range of range of Ej is Wj, and we see that alpha is equal to alpha 1 plus alpha 2 plus alpha k. This means that this is equal to, since alpha 1 belongs to range of E1, so I can write down E1 alpha 1, I can E1 alpha plus E2 alpha plus Ek alpha. So, this implies the identity operator equal to E1 plus E2 plus Ek. So, we have a relation like identity operator can be written as sum of operators E1, E2, Ek please. Now, we see that if V be a finite dimensional vector space and if V is a direct sum of subspaces W1, W2, Wk, then one can have projection operator E1, E2, Ek, where Ei satisfy the conditions like Ei into Ej equal to 0 operator for I not equal to j, and I equal to E1 plus E2 plus Ek, and the range of Ej equal to Wj. So, now let me see, if I suppose a projection operator E1, E2, Ek are given and these operators E1, E2, Ek satisfied the conditions like I equal to E1 plus E2 plus Ek, second Ei into Ej equal to 0 for I not equal to j, and range of Ej is equal to Wj, then is it possible to say that V will be direct sum of W1, W2, Wk? I mean V will have direct sum decomposition of W1, W2, Wk? Is the question please. So, let me write down these questions in a proper form please. This is some sort of theorem please. Let V be a finite dimensional vector space over the field capital F. Let V is direct sum of subspaces W1, W2 and Wk, that is capital V equal to W1 plus W2 plus Wk. Suppose this is given to us. Then there exist k operators E1, E2, Ek such that Ej square equal to Ej 2 Ei into Ej equal to 0 operator for I not equal to j. 3 the identity operator equal to E1 plus E2 plus Ek, and fourth range of Ej is Wj. I mean to say Wj is the range of Ej. Okay. Now, conversely, if there are k operators E1, E2, Ek on V, where V is a finite dimensional vector space, over the field capital F. The operators E1, E2, Ek satisfy the condition 1 to 4, condition 1 to 4, then V is direct sum of W1, W2 and Wk. So, the problem is like this: if V is a finite dimensional vector space over the field capital F, if V is the direct sum of subspaces W1 to Wk, then there exists k linear operator E1, E2, Ek, which are basically projection operator on V, satisfying 4 conditions like what we have given here. Now, conversely, if there are k linear operator E1 to Ek on the vector space V satisfying condition 1 to 4, then V will be V will also direct sum of subspaces W1, W2, Wk please. When V is direct sum of W1, W2, Wk, already we have seen there are k linear operators E1, E2, Ek, which are basically projection operator of V and satisfying condition 1 to 4. So, the first way on one part is done. Now, we are going to prove the second part, that converse part. So, I am going to prove the converse part please. So, given there are k linear operators E1, E2, Ek satisfying one to 4, claim V is direct sum of subspaces W1, W2 and Wk. We have for any element alpha belongs to V, alpha equal to alpha 1 plus alpha 2 plus alpha k, where alpha I belongs to Wi. This is because it is given to us I equal to E1 plus E2 plus E3 plus Ek. So, Ei as projection operator, alpha operating on Ei, it will give me alpha I which belongs to Wi. So, that is why any element alpha in V can be written as alpha 1 plus alpha 2 plus alpha k, something k component type of. So, this implies if I apply Ej operators, projection operator Ej on alpha, I am getting what? Okay, this is also equal to E of E1 alpha plus E2 alpha plus Ek alpha please. Okay. Now, E j alpha will be what? E j into E 1 alpha plus E j to E 2 alpha plus E j E k alpha. So, I will have like this thing. So, this implies E j E 1 equal to 0 operators according to given conditions 2. So, I will have simply E j square alpha, which is equal to E j alpha, which is equal to alpha j. So, for any expressions of the form 0 equal to alpha 1 plus alpha 2 plus alpha k implies that E j operating on alpha equal to E j alpha 1 plus E j alpha 2 plus E j alpha k. But alpha 1 is equal to will have in the range of the E 1. So, I can say this will be equal to E j E 1 alpha 1 plus E j E 2 alpha 2 plus like this E j E k alpha k, something like this thing. So, it will basically I will have E j square alpha j, which is equal to E j alpha j, which is equal to alpha j. So, this implies 0 equal to alpha j. Okay. So, similarly, one can show that alpha I equal to 0 for I equal to 1 to k. So, this implies V is direct sum of subspaces W1, W2 and Wk. In fact, we are interested about the decomposition of the space as a direct sum of subspaces which are invariant under a linear operator, please define on the space, please. So far I have not used the direct sum decomposition of the space or direct sum of subspaces, whether subspaces are invariant under some operator or not, that we have not utilized or not discussed. But now I want to use this concept that the subspaces will be invariant under a linear operator defined over the space, please. Using this information you will see that it gives more simpler structures. Let V be a vector space over the field capital F. Let T be a linear operator on V. Let V equal to direct sum of W1 plus W2 plus W k, where W I is invariant under T. So, it is a invariant subspace of V place for I equal to 1 to k place. Now, let us see this information how it is helping to split the operator T. Now, consider the restriction operator, okay, restriction of T on W I, and let it be denoted, and let it is denoted by say T I. So, this implies that T I is basically restriction. So, T I is restriction of T on W I please. So, T I you will see the operator, linear operator whose domain is W I please. It is given for any alpha belongs to V, alpha equal to alpha 1 plus alpha 2 plus alpha k type, it is given to us. So, T of alpha equal to, I can say, T of alpha 1 plus T of alpha 2 plus T of alpha k, but alpha 1 belongs to W 1. So, here T of alpha 1 is same as your T 1 alpha 1 plus similarly T 2 alpha 2 plus T k alpha k. So, I can write down the image of any element alpha under T as sum of image of different component alpha 1, alpha 2, alpha k under restriction of T to W 1, W 2, W k. So, let us see what way this will be useful. Okay. So, for this let me consider a example please. Let T be a linear operator on a finite dimensional vector space V, and V is equal to direct sum of W 1, W 2 and W k like this. Let B 1, B 2, B k be the basis of W 1, W 2 and W k respectively. Given that W I is invariant under T. So, this implies if I consider T I, which is basically restriction of T on W I, let dimension of W I be D I. Then the matrix representation of T I with respect to B I will be a square matrix something like this. This is D I cross D I matrix over the field capital F. Okay. So, this implies if B equal to B1, B2 and Bk, then matrix representation of T with respect to B will be of the form of like this. This is, say, let us consider A1, which is a D1 cross D1, then again I will have some new second matrix, say A2, D2 cross D2 and AK DK cross DK type. So, I will have the matrix representation of T with respect to order basis B equal to like this. So, we see that through this example, when the V is the direct sum of W1, W2, Wk and each Wi is T invariant, then the matrix representation of T is a diagonal matrix, where diagonal entry is basically again each of them are square matrix of the size di cross di type. So, it is a very simplified structure. So, definitely this structure is much simpler than the, if I consider full matrix please. So, we will see that how this invariance concept help to simplify the operator T please. This will discuss in the next class please.